Okay, Rach. Yeah. Welcome again. Another Hertfordshire Building Control CPD webinar. Delighted, as I said, to see such a big audience again. Today, the subject is retrofit insulation in buildings, and that's focusing on internal insulation in this case. As many of you know, we've got new regulations coming in soon. The new approved document L will be hitting the shelves in December of this year, we hope, and will be coming into force in June 2022. And what that's going to be doing, we know already, it's going to be tweaking fabric efficiency standards for new buildings, and also, of course, for extensions. And that will be an interim step. It's not the full step, but it's an interim step towards the Future Home Standard envisaged for 2025. And then that in itself is leading forward to the ambition for zero carbon in 2050. And be assured, we will be covering those and other changes to the approved documents and building regulations in a future CPD webinar event. But we might think new buildings and the ensuring standards in new buildings, that's all very well, isn't it? But what about the existing building stock? How do we get that upgraded? Because that's all emitting a huge amount of carbon into the atmosphere, isn't it? And we know from bitter experience in recent years that doing that, it must be done sensitively to the buildings being worked on. Otherwise, it risks deterioration of the building fabric and unhealthy living conditions. So here to speak to us about that, I'm absolutely delighted he's managed to find time to talk to us about these issues, is Andrew Mitchell. And I'll just read to you his brief biography that he sent me. For over 25 years, Andrew has developed a passion for the built environment and its interaction between people and the wider environment. His work has led to bringing new solutions to the mainstream construction market, with a particular focus on the thermal performance of buildings. Andrew's been a company director with many organisations and currently oversees manufacturer of zero carbon modular buildings and a consultancy. And the consultancy works with a wide network of businesses and organisations, and that includes the government's Department for Business, Energy and Industrial Strategy, as it's now called. Quite a mouthful, isn't it? And he's provided advice to them on building physics and its importance within the commercial market. So I've seen this presentation and I can assure you it's very thought-provoking, especially for somebody like me, you know, who's been in the building control profession for a lot of years. And it made me think, you know, are we really doing things properly in applying the approved documents as we do? See what you think. Andrew, take it away.
Thanks, Trevor. Much appreciated. Not nervous at all after the high bar you've set me, but there we go. So yeah, hopefully, as Trevor said, hopefully this is useful to you. Don't want to waste your time at all. As Trevor said earlier, please put questions and stuff in the chat. I'll stop a few times in the middle if we want to catch up with questions and stuff. So we can take live questions as well, which Trevor's going to field. Yeah, let's dig into this and hopefully, like I say, hopefully it's of use to you. So I'm just going to get my screen sharing and we'll kick off. Hopefully you can see that quite clearly. Okay, so I was asked to speak about internal wall insulation, the pitfalls and hopefully some of the solutions. And obviously internal wall sill insulation as a solution, not the solution, just one of many solutions in trying to reduce the heat load that we need to apply into our buildings to keep them warm in the winter. Obviously, if we do that, we reduce the amount of energy we're using, and while we still have a grid that does use fossil fuels, it is being decarbonised slowly, and there's been some great progress made with things like offshore wind and so on. We've still got a way to go. So anything we can do to reduce the energy is key. And it's worth noting, actually, even today, despite all the technologies that we've come up with, the reduction in PV panels in terms of their cost, the pushing forward of heat pumps and stuff, And I'm not knocking any of these technologies necessarily, some are a bit flawed, but the most cost-effective way of reducing the amount of CO2 released into the atmosphere is actually still to reduce the amount of energy we're using on our built environment. So we're going to, and again, as Trevor said earlier, I'm sure many of you are familiar with the 2050 target. So trying to reduce our CO2 emissions by 80% on 1990 levels by 2050. So whichever way you cut it, we're looking at our existing building stock. About 75–80% of our current building stock will still exist by 2050. So we've got to do something about what we've already got, and we've got 9 million solid wall homes in the UK, you're going to have to find some way of treating those, and cavity wall insulation clearly is not an option because there aren't any. So these are the areas we're going to try and cover. Multifunctionality of insulation, U values, Y values, airtightness. The reason why I want to go through the basics is because hopefully it kind of, I don't want to teach you suck eggs, and some of you will be well ahead on this, but it sometimes helps just to have a bit of refresher and maybe at least all put us on the same page. Moisture control in buildings, that's a bit of a key one. A bit of design guidance, and the sponsors of today is a company called Unity. So we'll provide some solutions that they do at the end, but I would sort of add the fact that, you know, this is one example, and there are others out there, but the key thing really is they're very good illustration of making sure you're following sort of first principles, if you like, in terms of internal wall insulation. So they're a very good illustration. So quick run through. Multifunctionality of insulation. I don't know if that's ever struck you before, whether you've actually thought maybe insulation plays a greater role other than just keeping heat in the winter. But I suggest it does, as with this little infographic here. So just taking you through it, obviously there's thermal. Acoustic plays quite a significant part. Particularly on either lightweight structures or rooms in roofs, where again that's a lightweight structure in essence, but I was thinking more of timber frames initially. There's a whole thing about fire, obviously post Grenfell. We've finally kind of woken up to the importance of it, but insulation plays a key role in that dynamic. Something also we'll tease out, particularly when we come on to moisture later and the control of moisture in the building fabric. Health and comfort actually is directly related to the thermal performance of buildings and therefore to insulation. And then there's some practical elements in terms of buildability, particularly when it comes on to things like airtightness. I've seen some origami in my time in terms of people trying to reduce the amount of air leakage with membranes and tapes, durability, and of course we shouldn't forget a key part of any design should be how are we integrating this with our general sustainability, the planet at large. So the two key ones I wanted to focus on really is thermal performance, because that's obviously what we're trying to achieve here. We're trying to reduce our heat load to the property, and also this thing called breathability, which is a bit of a misused term, I think, but hopefully we'll try and find a way of defining it between the two of us. So thermal performance first. So any building at all will lose heat in three primary areas. Okay, so we might describe these in terms of airtightness. So that's the amount of air that literally leaks out of the building, and obviously the more warm air that leaks out of the building, the more heat we need to keep it warm. U values, I'm sure that's the term you're familiar with. So that's the amount of heat that's losing through primary areas or principal areas such as a roof, a wall, a floor, windows still count as a big primary area, doors and so on. And then Y values. Normally at this point I'd say please can you put your hands up, but we're not in the same room, so we'll skip that one. But Y values, as in who's heard of this before, and usually there's a handful but not that many. Y values are basically they're a notional value, but they're used to measure the amount of what we call non-repeating thermal bridging, and I'll give a little bit more detail about that in a minute because it's key. So U values, just important recap in reference to the built environment when it comes to retrofit, because I think we all kind of know building regs, you know, sort of 0.3 default backstop, 0.28 U value is kind of heading the direction. We've heard of U values maybe with passive house of 0.15 or below. But I think we forget actually where perhaps that measure comes from. So it's worth actually looking at that in relation to older properties. So and maybe doing a little recalibration on U values. So here we've got a solid 9-inch Victorian brick wall. Typical U value is probably about 2.14, so that's quite a lot, as in quite a lot of heat is leaking out of that. If you look across to your right, that's about 4,280 joules per second. That's when your temperature is 20 degrees inside and 0 degrees outside. At the risk of stating the obvious, if the temperature is 10 degrees outside and 20 degrees inside, it's going to be less because you're not having the same heat loss parameters. Now, if we stuck just 40 millimeters of, say, wood fibre insulation onto the inside wall, we actually reduce that heat loss significantly by actually about 67%, which may or may not come as a shock to you. So we reduced the U value from 2.14 down to 0.7. And just to sort of throw in a few more, just to kind of get it in context. So if we stuck 60 mil on, we've hit an 80% target. 100 mil, we're down to 84%. Interestingly, the passive house. So if we were aiming at 0.15 that I mentioned earlier, and that's passive house new build, not a standard called Enefit, which you may be familiar with, which is slightly more relaxed, which is effectively passive house for retrofit buildings, would effectively, if you were to measure it against our starting point, is 93%. Now, obviously, that is still a significant saving, but it's interesting how we often sort of think in ourselves, you know, even the U value there of 0.34, we say, well, that's missing building regs. That's crazy. That's not very good, is it? But in reality, you're reducing your heat load from where it was originally by 84%. Okay, so it's really significant. So I'm not saying that you should not go for a lower U value, but there are reasons why just focusing on U value can be really unhelpful, and we'll come on to those later. But one of the key things I wanted to start with this to hopefully just provoke us a little bit away from just focusing on U values, because the message really here is it's not all about U values, and you achieve quite a lot even without hitting building regs, and I think that's quite important. So quick overview on U values there. Y values, and so sorry, I'm assuming everybody knows it, just in case you don't. So U value, like I said, primary area, so a wall, a roof, so on and so forth. It should include all the repeating thermal bridging. So a roof is a good example of this. Roof, you've got rafters, so pieces of timber. You've then got gaps between the timber, which are usually filled by insulation. You've then got maybe membranes and battens and so on the top with your slates or your tiles. You may have some more insulation on the underside. And here I'm obviously describing to you a warm roof where you've got a room in the roof. A U value should have included all that timber, okay, because it's puncturing the insulation at regular intervals. So that's called a repeating thermal bridge. So the reason why I've said and that the U value describes all the heat loss through all those components. Y value, this is for non-repeating thermal bridging. So this is typically the interface between two primary elements. So as you see from the diagram on the right, it's the roof and the ridge and the wall. It's maybe the wall and the window and so on. And typically you will have additional structural elements that come into play, or thicker sections of building elements, which just mean you're going to get more heat loss at that particular junction. And on the left, we've got a little section there, which is a plan view through a window. So a window reveal, I should say, and a window. And if you can see my arrow on the screen, what we've done here is we've actually put some insulation on the inside. So this is the inside of the property. Outside is where it's getting purple. You've got a calibration chart just down the side here. That's whenever you see a thermographic image, always just check out the old temperature there. It's funny how sometimes they calibrate, you know, if you change this, just I could set this if I wanted to say between 5 degrees and 0 degrees. It can present quite a convincing picture if somebody's trying to say, you look at this house, it's doing really well. And it's funny how the bush in the front garden is actually performing quite well, energy efficiency as well. But there we go. The point here is we've put some internal wall insulation in. We've tucked it into the reveal. That's an important detail we'll come to later. But you'll notice the temperature 20 degrees is no longer, this red line isn't appearing, okay, on part of this window, okay? And that's simply because too much heat is moving it out of the building, so it's not maintaining the heat of that material. So this area you would class as a thermal bridge. And a Y value is effectively this detail multiplied by the length of that detail. So in here it'd be the window reveal. The same calculation done for all these other junctions and multiplied by the length of the detail. You add them all up together and that is your Y value. So it's a total heat loss, a notional value of all the heat being lost through these non-repeating bridgings. Now this is quite important now when it didn't used to be. So if we imagine that big square there, both the blue and the red, is the total heat loss through our building fabric. And when we had our old Victorian wall, it was most of that heat, we'd imagine the roof isn't insulated either, is getting thrown out through our principal areas, okay? And a small amount is being lost through our non-repeating bridging. If, however, we tackle our U values and reduce that heat loss down to roughly the high end of building regs, so about 0.3, that ratio changes significantly. So you can now lose as much as a third of your heat loss on non-repeating thermal bridging as you can with the rest of the property. So it's a big area. This is particularly relevant in new build because they don't pay enough attention on detailing, and as a direct result you get greater levels of heat loss when you didn't need to, and there are good solutions out there that avoid that. With retrofit on solid wall insulation, it's a slightly different story, just because of the level of non-repeating bridging you get, and I'll come on to that in a second, but it's still an important main. I'm hopefully just trying to say, look guys, again, what I said earlier on is not just about U values. Think about Y values, think about this non-repeating thermal bridging as well. So now if we bring these two together, an interesting thing starts to happen. So quick graph afternoon graph here. Okay, along the bottom we've got thickness of insulation, okay, starting at 0 obviously and running up to 140, and then up the side we've got rate of heat loss, okay, in joules per second Kelvin. So if we've got a heat loss out the wall on a given day at a given temperature differential of, say, getting close to 120, so probably about 115, with nothing other than the wall itself. If we stick 20 mils worth of insulation in, we pretty much half that heat loss, okay? You stick another 20 mils worth of insulation on, you quarter that heat loss, okay? You don't halve it again and get to 0, obviously, because you'd just be defying laws of physics. And you can see the point here is the more insulation you add, you will always reduce the heat loss. But clearly, the amount of heat loss that you achieve is ever decreasing. It's a parabolic curve. And you're seeing it sort of level out sort of around about 80, 100 onwards. And so the question is, particularly with internal wall insulation, but this could include external, it could also just include a new build wall. Every time I'm adding another 20 mils worth of insulation on, I'm increasing my footprint on my wall. If it's internal, I'm decreasing the footprint in my room. If it's external, I'm decreasing the footprint on my, and what am I really gaining here? So you need to play those two off each other. If we introduce Y values, however, so our non-repeating thermal bridging, the picture changes slightly. It does if I press the right button anyway. So what's happened here is this is the rate of heat loss with thermal bridging, whereas the blue line was purely based on U values. And the point here is actually, particularly, and this is internal wall insulation, with internal wall insulation, the rate of heat loss increases much more because we have much more thermal bridging. Think about your window reveals, which I showed you earlier. You have to insulate them for reasons which will become obvious shortly, but you cannot usually, without some major works, put the same amount of insulation that you've just put on your wall, okay? And also, you've got a lot of windows, so that's a lot of windows. You've got other details around doors. You've potentially got slightly more tricky details in terms of intermediate floors and so on. And when you factor those in, you'll basically find that our line is leveling out much earlier, so it's even less helpful to start chasing the U value and going for thicker amounts of insulation. So I hope that makes sense. But again, this might sound a bit strange because it's like, hang on a minute, I thought he was trying to teach us how to save energy here, and he seems to be just suggesting, no, wait a minute, it's not at all. What I'm trying to say is, if you focus on one area, you'll probably not gain that much, okay? It's actually having a more kind of broader and rounded design approach, which leads me on to this subject, which is probably the most important subject, more than the thermal performance, simply because when you change the amount of thermal performance in a building, when you add insulation to a building, you literally change the building physics. You change the way in which it behaved previously, and that's against a new build over a previous new build design, or in this case, a retrofit property. And we need to be aware of it. And one of the essential ways, amongst others, that we need to be aware of it is this area called breathability. So probably help with a bit of a definition. So when I'm talking about breathability, this is what I'm talking about. I'm talking about something called vapor permeability. So that's moisture as a gas, and how that gas moves through a material. Okay, so the moving through is the permeability part, the vapor part is the gas. And I don't think we're familiar with thinking as moisture as a gas. We're quite happy with thinking about the idea of oxygen as a gas, and you know there's oxygen in front of you, not least because you're breathing, but you perhaps aren't as aware that there's moisture in front of you as a gas. More detail in a minute. Next one, so breathability I would define as 3 areas: vapor permeability, capillarity, so that's the ability of being able to move liquid moisture within a material. Again, I'll cover these again in a second, just always good to repeat, isn't it? And then the final one is hydrocapacity, and that's the ability of a material to take up and let go of moisture, the speed with which it does that, and not just as a liquid, but also as vapor. Okay, so I'll repeat those in a minute. And I think, as I mentioned a second ago, we're quite unaware perhaps of the prevalence of moisture. And frankly, it's all around us, never mind the fact that we're, however much percentage we are as a human being, I couldn't tell you actually, off the top of my head, it's a lot though, isn't it? So we're pretty familiar with this stuff, particularly at the moment. We're a little bit more familiar with this stuff, and sometimes people say that's moisture vapor, which it isn't actually. That's moisture droplets, which are condensing in the air because it's so hot. But a lot of what's around it is moisture vapor, which brings me on to this sort of moisture vapor, which we're less familiar of. I think the closest we ever come to being aware of it is when we start saying, "Oh, it's a bit muggy in here," classic phrase. It's a bit muggy in here. Can somebody open the window, please? Which is interesting, because actually that is probably the most effective thing you can do in terms of controlling the mugginess, which is really just a high level of relative humidity. That sounds a bit more waffly, doesn't it? It's a bit high level of relative humidity in here. Stick with muggy. But the point is, it's the relative humidity is higher than it usually is, and that has a massive dynamic on our health and on our comfort, which I'll come on to in a minute. So, bit of a historical look, which I think is helpful, and how this comes together previously. So basically, we've been building houses for quite a while. Most of the stuff that's still standing is still standing because it worked. The stuff that didn't work, funnily enough, isn't standing anymore, and we kind of perhaps forget that. Typical older properties used to be have high levels of ventilation. But what was also quite interesting is the moisture would move quite quickly often within the fabric as well. So a masonry wall, I'll come into that in a bit more detail later, but you get moisture movement quite effectively. The particular materials that we used were more ready to transport moisture around them. And I think we often don't give enough credit to older properties. Things that, for example, properties didn't always used to have damp courses. The reason for that is they actually understood where they were building, like not in floodplains as a minor detail, but even there they would understand more about the groundwater, where the water table was. They'd check for underground streams and stuff to make sure that you weren't going to have issues later on. Now obviously with bits of climate change, this could become a problem where you didn't have a problem before, but it was still they were much more aware of this, and having fires inside the houses with big chimneys, you get a massive regular changing of air being drawn through the room, through the fabric from the outside. It was cold in winter, and it was, you're more likely to get killed with pneumonia than you would today. But it was a kind of different dynamic, and I think we forget how old it was. We forget other details. If you've heard me before, I might mention this before. So, the classic thing with furniture. So those high wing chairs that we've got, at head height, they weren't to stop Grandad falling out of his chair when he fell asleep. They were actually to keep the heat in. Literally, you'd sit around a fire and that would actually bring the heat, the radiant heat from the fire, and keep you more warm. If you put your hand around the back of the chair, as a previous next door neighbour who's quite old now would tell me, it was freezing. You know, he would describe himself getting dressed in front of the fire as a kid because it was freezing everywhere else in the house, and then you'd leg it to bed and jump under the eiderdown and kind of shiver yourself to sleep. And just as a kind of historic thing, I would ask this obviously and expect an answer, but we can't do this with Teams. But average temperature, quick guesses on the average temperature in the UK in winter in a home in the 1970s. And the answer to the question is about 13 degrees C, believe it or not. So cold, right? Not as cold as if you're in Germany, which is an interesting point that I might pick up later, but or Italy for that matter. So the reason why I'm labouring the historic stuff is because we are aware that we need to try and move to a slightly different built environment. The reason for that, the main driver for that would be comfort. So we had access to very cheap energy, courtesy of fossil fuels, particularly in the late 80s onwards, really, particularly of North Sea gas, where we've been able to happily heat our homes, run around in jeans and t-shirts in a sort of balmy 22 degrees C or whatever in the winter, not really worrying about it. And the reason was because the energy was so incredibly cheap. What we've now realised is we're kind of screwing up the environment a bit because we're releasing huge amounts of CO2 that have been happily locked up for millennia or longer. While at the same time, we've managed to burn through these reserves of gas in a frighteningly quick speed. So I don't know if you know this, but we actually now import more gas than we actually pull out of the North Sea. We peaked our North Sea extraction of gas in about 2000, and 20 years on, we're now importing at least about 60–65% of our natural gas, usually liquefied, usually in big container vessels with domes on. You might have seen them from stable parts of the world like Qatar and stuff like that. So we have to try, both from a commercial point of view, we need to reduce our heat loads because we can't be as reliant on fossil fuel, but also because of the climate change issue, which is clearly quite real. So one of the ways to do that, as I've laboured earlier, is reduce the amount of heat that gets lost through our fabric. And the key thing that when we do this, again, to make the point again, is we need to be very aware of what we call unintended consequences. So the fact is, just to repeat it, if you add insulation or any kind of thermal performance dynamic to a building, you will change the fabric, the dynamics of the building, the physics of the building, and you need to be aware of that so you don't end up with bad consequences like this one. So here we have some timber frame buildings that were built in the 60s, late 60s, 1967 exactly. This is a study done by BRE Wales. They were insulated in 2006. So it was a closed cell PIR foam product that was wrapped around the outside of the property, which significantly improved the thermal performance of the building. They were very cosy for about 4 years until they started noticing they were shutting the doors internally and the walls seemed to wobble a bit. I joke about it, but it's really it's tragic because these properties have now been levelled. They no longer exist because there was structural failure as a direct result of dry and then wet rot, which was a direct result of wrapping a closed cell insulation around a timber frame. Moisture could not escape and the timber gave way. Thankfully, nobody died, but I still wouldn't fancy getting kicked out of my house. Thank you very much. So in order to get our heads around this, in order to understand moisture in general and how we deal with it in buildings, again, let's just go through some hopefully basic building blocks, but like I say, hopefully it gives us a clear picture. So two sources, pretty straightforward stuff here. External, hopefully familiar with those. Don't just think about the stuff that's falling out of the sky. It is about streams and stuff and how they might or might not flood. That can affect all sorts of things, as I mentioned earlier, in terms of water tables or even just localized flooding. And then internal, and again, lifestyle change, massive. We forget. I live in an old Victorian property, and it certainly wasn't a pauper's cottage, and there was a WC down the bottom of the garden. There was no water effectively inside the house. This is what we get these days. We've got umpteen, how many bathrooms, ensuite bathrooms, umpteen toilets. We've got washing machines, we've got all the cooking. Some of us dry clothes on the radiator, that doesn't exactly help. But just to give you an idea here, these are internal moisture sources from a typical family in the UK and where it's derived from, with a grand total there at the bottom of somewhere between 9 to 15 litres. That's moisture moving into the air. That's not what goes down the plug hole. That's actual moisture load that, because of these activities, ends up in the air. So we have to do something about that. We can't just ignore it. I know, skip that. So I want to touch on this later. I've just remembered the order of my slides wasn't what I thought it was. I want to touch on this later. This is the important thing here, and it's important to make a distinction. The important thing here is to control the amount of moisture in the air through proper ventilation. Okay, and when I say proper ventilation, that can vary massively, from opening a window to having some, you know, fully plumbed in mechanical ventilation with heat recovery system, so MVHR. It's not down to ventilation, doesn't just mean an extraction fan. It's a bit broader than that, but we do need to control the amount of moisture, what happens to that moisture once it's in the atmosphere, and we need to do that through ventilation. But I'm going to go into that detail in a minute. What I want to do though is talk about the effect of that, what you've just seen there on the building fabric. And while the main talk today is about building fabric, you can't really separate the two without talking about a little bit about ventilation, but like I won't go into too much detail. So let's look at an actual wall in terms of the, so we've talked about the fact you get moisture internal and external. Let's talk about context. So again, internal wall insulation, we're only generally going to fit internal wall insulation in most cases on a solid wall. Okay, you may do a combination of cavity and internal, but that's unusual, and you do want to be careful, particularly in terms of where that property is located in the country because of driven rain. Put my teeth back in again. We'll touch on that later. So this is the dynamic on a wall. So let's assume there's your wall in the middle. On the right hand side is our internal space. On the left hand side is the external space. Temperature, you may or may not know this. Temperature, the best way to think about it, or energy, I should say, it tries to level itself out a bit like water. So if you've got 20 degrees centigrade on the inside of the house and 0 or anything below 20 on the outside of the house, that 20 will try and level itself off and the 0 will try and level itself up. Obviously, there's far more air at 0 outside the property than there is on the inside. So most of that heat energy is going to go through the wall. OK, which I think we all accept. When it does that, that effectively creates a kind of pressure gradient in terms of moisture. And effectively, it's dragging that moisture vapor. So this moisture as a gas, the water as a gas, through the wall. And we call that internal vapor pressure. OK. In addition to that, so these are the dynamics acting on a wall. In addition to that, we'll get rain on the outside of the wall. OK, and brick is not waterproof. Let's not forget that. It's porous and it will saturate. That's why we used to, and still do, render buildings, but I think we've forgotten again, we didn't render buildings to make them pretty. It was quite a practical reason. It made it more water resistant, not waterproof, water resistant. So you had less moisture saturating the brick and therefore less risk of moisture getting through the wall. Now in you know, reasonably mild climates, which is what we have in the UK, with relatively low levels of driven rain, so kind of areas like Cambridge or Oxford or somewhere like that, certainly anything east is generally fine and you don't need to start render. Whereas the further west you go in the UK, you get higher levels of driven rain, and obviously you get it on the coast, which again is why we often end up with coastal buildings that have render on. Now what happens next is perhaps more or less familiar with people in terms of the dynamic, is the sun comes out, which seems a bit bizarre because what's that got to do with moisture? Well, what happens is we get something called reverse vapor pressure gradient or reverse diffusion. So we've got our saturated brick. A lot of that moisture will evaporate as the sun comes out, but some of it will actually get driven into the brickwork. OK, so during the summer, in fact, from spring on, you generally find that the amount of moisture in the building fabric is on a solid masonry wall is increasing. OK, whereas you'd almost think it was the opposite because the sun was coming out more. Certainly after a period of rain, which we kind of have a bit in the UK. The final one, which we mustn't forget, is Construction moisture, so anything we do to a building from a construction point of view, whenever we're using wet trades, actually brings buckets literally of water into the building, and that's got to disappear at some point. So we need to think about that. But also ground moisture, stuff that's coming up from the ground. Again, the context here is solid masonry walls, so stone or brick. You're going to have potentially moisture coming up from the walls. It may have a DPC, the DPC may be breached, it may not have had a DPC, and it didn't need a DPC because it may have worked in equilibrium. We'll touch on that in a second, but it's something that we need to be aware of. So now looking at the picture of our pretty wall before we started, and I've got the graffiti all over it, it's far more complex. This is quite a dynamic thing that's going on here. Somebody said to me once, moisture in building fabric is not rocket science, Andy. It's way more complicated, particularly actually when you understand that you can literally have moisture as a vapor moving from inside to outside and moisture as a liquid moving in the opposite direction at the same time. At least with a rocket, it just, energy out one end and off it goes. But it's worth noting. And so I'm just going to touch on this again because it's kind of a nice point to just do a quick refresher on this. So quick one on the terms again. So we've got vapor diffusion. We mentioned that at the beginning. So this is water as a gas. OK, you can't see it, but it's there. You've got liquid flowing through a material when it's porous. And we refer sometimes that as to capillary flow, but not entirely, because capillary also is about draw. Liquid flow through pores of a material can be water and gas, not just liquid, which is, we forget this sometimes. Capillary flow is just liquid. So think of two pieces of material on your desk. You've got a piece of plastic sheet, you've got a piece of blotting paper, drop on each. Hopefully you've got it already. Drop of water on the plastic will stay as a blob. Drop of water on the blotting paper will dissipate quite rapidly, and you'll get quite a large circle of water. Important point to note, the surface area of the blotting paper, which in this case is on the right, is actually going to dry out a hell of a lot more quicker than the drop of paper on the plastic. Why? Because you've got much more surface area. That will come out later, but it's an important dynamic to remember. And it's also about transport and transfer of moisture, which is also another really important dynamic when it comes to any insulation. Then we've got air movement, so that can be generally water as a gas. And then we talked about this hydrocapacity or hygroscopic buffering. So this is water as both gas and liquid, and how quickly it absorbs it and how quickly it lets it go. So great examples of very fast hygroscopic materials are interesting clay, so unfired clay. Believe it or not, anybody who used to live in a cob house, so that's when the walls are made of clay and straw and a bit of dung thrown in for good measure, that were built up, in shuttering and stuff. They do not suffer from condensation on the windows because the fabric sucks up the moisture really quick out of the air and then lets it back out into the room as the equilibrium changes. So it's quite neat. You can actually do this. I had to play with this once in a bathroom, and there's modern clay plasters you can get out there. So there's some amazing stuff. In fact, there's a company called Clayworks down in Cornwall, and they do some remarkable stuff with clays, all sorts of colours and stuff. And it's so long as you've got a base coat to clay and then you skim, what you find is it buffers the moisture in the atmosphere. You still need to ventilate it. OK, breathability. I'm just going to put this footnote in if I forget. Its ability has got nothing to do with moisture getting out of the building fabric. Now the next sentence is the key. Moisture getting out of the building fabric to regulate the internal moisture levels. It will do it, but at such a tiny level it's not worth worrying about. Moisture just needs to get out of the building fabric. That's the key part. We'll come on to again in that in a minute, but it's ventilation that needs to control the moisture that's in the air, or the moisture that you're putting into the air from the various activities. Don't confuse breathability with a way of controlling moisture in the air. OK, before I go on to the next bit, I was going to stop earlier, but I must have got carried away. Have we got any questions so far, Trevor, or are we all good?
I don't think there's any questions, Andrew. I'm getting a bit of echo, which is unfortunate, but I'll struggle.
That means we've all fallen asleep. Quite right. It's far too late in the afternoon, or something else. That's fine.
I would make an observation, though, if I may.
Yes, please.
very interesting you talking, and I found that last time, the law of diminishing returns on insulating internally in something like a Victorian solid wall.
Yeah.
Because in building control, if somebody wants to do that, that's controlled as the renovation of a thermal element, and we impose standards for the insulation, and we insist that you achieve a U value of 0.3, which is quite a lot of insulation, and internally it's going to result in quite a lot of loss of floor area and potential problems. So the question to you is, do you think the building regulations are a bit too heavy-handed in that respect, and is that possibly stopping a lot of buildings being renovated because of the requirements are so onerous?
Yeah, no, that's great. That's a great question. That's a great question, actually. So the truth is, no, I don't think they're too heavy-handed, because actually there is a provision within Part L which allows you to relax the U value for internal wall insulation up to 0.7. So long as you can demonstrate that the building itself won't, you've got to come up with a reason. You can't just say I don't fancy it. But if you can say, well, look, actually, I'm concerned about the risk to my property, which is a big one, and really this is where the moisture thing is so key, which is why I'm labouring the point so much. If there is a risk to the property, or the one you mentioned, I'm going to lose way too much of the floor area internally, which isn't often the case, to be fair, because usually it's only one wall normally. It's rare for sometimes two, rarely three. But if it's four, then maybe you should be moving house. But I think so I don't think it's the regulations themselves, actually, Trevor. I think it's actually the way they're applied, and often that provision. Sorry.
Well, you say that, but this 0.7 is a threshold value. So if your wall is inferior to that, then you are obliged to upgrade. And as you say, if it's not technically feasible, then we wouldn't ask for it. But the idea of loss of floor area is a subjective judgment on what is feasible or not. So
absolutely, yeah, no, absolutely. I suppose what I'm thinking is 0.7 actually isn't particularly onerous, as we showed earlier. 40 mils will get you below that quite comfortably. It's more to do with I think often a lot of, particularly, say, no disrespect to contractors or anybody else in the industry, if folk are unaware of this, they're unaware of it, and this is part of, I guess, almost part of what today is about. Is it's all about discussing these things, educating ourselves in the information we've got so far, hopefully applying that information and learning, and then teaching each other, really, because again, just contextually, let's not forget, it's only the last sort of 3 or 4 decades that we've really begun to get our heads around thermal performance generally. In the UK, I might add. In Scandinavia, you have to do it because you'd be dead otherwise, because it got really cold in the winter. And we also forget how mild the climate is in the UK. When our cousins from mainland Europe come across and say, oh, I can't believe you've still got single glazed windows. And it's like, well, yeah, because it doesn't get that cold. In Italy, it's minus 14 degrees in the winter. And that's the Mediterranean. In the UK, it goes minus 14, and we're all talking about it. And I think we forget that it's not as cold. Germany's freezing. I've mentioned this earlier, freezing in the winter. And we forget these things. And therefore, they've kind of just got on with the dealing with it, not because perhaps they're ahead of us in terms of sustainability or climate change, although obviously that's put them in that area, that's put them a step ahead. But the default was mainly about comfort and survival, and the fact that they just couldn't get enough energy, and the energy wasn't as cheap as what we had dragging it out of the North Sea. But I've completely gone off piece to your original question, and I guess the point, going back to your point, is that the 0.7 backstop, if a lot of contractors are unaware of this, some building control officers are less aware of this, or see it as an absolute, no, you've just got to get to 0.3. And I'd say when it's internal wall insulation, you don't really want to drive it that far, because actually getting from 0.4 to 0.3 of a U value, we mentioned the Y values earlier, you're not getting that much. No. You're probably not getting anything. In fact, I'll give you a random example. If you had a standard wall and you put 100 mils worth of insulation on it and nothing on the window reveals, now you wouldn't want to do that for other reasons, but let's just assume you have, purely from a heat loss point of view. That wall even though it's got 100 mil on, would perform worse than with a wall with 40 mils of insulation on and 20 mil on the reveals. That's how important the non-repeating thermal bridging is. So if you just pursue this U value, it's like it's pointless. So this is a great question. Sorry, long answer.
Yeah, good food for thought for the building control people out there. Anyway, I've digressed you too much.
No, it's my fault. So I just want to get our heads around. Now, if you can get your head around this is brilliant, because it's sort of tricky, but it's important. So this relative humidity thing that we keep mentioning, okay, RH, relative humidity. So it's relative because it's the amount of humidity, and it's relative to the temperature. And it's simply because of this. So I've got 2 cubes of air here, cubic meters of air. On the left, I've got a cubic meter of air, which is 20 degrees centigrade. That's how warm that air is. And on the right, I've got a cubic meter of air that's only 0 degrees. Okay. And basically it's saying, look, warm air holds more moisture than cold air. And those are the figures there. So at 20 degrees C, the maximum amount that air can hold is 17.3 grams. Whereas if you cool it down, it can't hold as much as that. It holds 4.8 grams. And this is the point. As air changes temperature, therefore, its relative humidity will change. And when the air goes from warm to cold, the relative humidity goes up. So it increases in percentage terms. And when it warms up, it goes down. So if you take a room at 20 degrees C and 50% relative humidity, and you start to cool that air down, you'll see that 50 start to dial up, 51, 52, 53. And eventually, when you hit 9 degrees C, so a little over halfway, you'll have seen the relative humidity go all the way up to 100%. And at that point, the air can no longer hold, if it goes any colder than 9, it can no longer hold any more moisture. And so it just lets it go. Okay, that's how we have rate, funnily enough. You know, the warm air rises, it cools down, because it's super saturated with moisture, it goes up to 100%, it falls out, simple as that. And obviously you've got air levels moving, and some are cold and some are warm, but anyway, that's why it runs. If you apply that to buildings, that's why we get condensation on our walls and our windows. So it's not the air hitting the window that means we end up with condensation. It's because you've got warm air, use the example again, at 20 degrees C, 50% RH, comes in, moves into a gap that's just in front of the window that's much colder. And we're talking microscopic bits here. We're not talking big millimeters. We're talking fractions of. And as it moves into that space, if the temperature outside is quite cold and it's single or even in some cases double glazed, the temperature of the glass will be colder than 9 degrees. So the temperature of the air will be colder than 9 degrees just in front of it. So as that warm air moves into that space, it cools down rapidly and sheds the moisture. And as it sheds it, sticks against glass. Same with the wall. That's why you get damp patches on the wall. And you know you've got a condensation problem because you'll end up with black mold on the wall. And black mold will only grow in pure water, in clean water. So which is why you get it in your bathroom, because there's a lot of clean water and a lot of moisture in general condensing around, and why you sometimes see it in other areas of your house, and you don't want it because it's really not good for your respiratory system. But that's another thing. But if you can get your head around that, then you've smashed it, basically. And I can stop now, actually. No, we'll carry on. But you'll hopefully then understand the implications, particularly when it comes to any building fabric, but particularly in terms of internal wall insulation. So I want you to try and kind of remember that over there. I briefly want to touch on ventilation and why it's so important again, and then we'll crack on with building fabric. So this is a really important graph. I don't know how many times I've shown it, but it still does my head in a little bit, actually, even today. So this is a graph showing along the bottom relative humidity from 0 to 100% from left to right. And then up the sides, you've got this charming lot, which is why we did do this presentation at lunchtime. And you've got, well, you can see what you've got. And what you will find is that that charming lot, depending on type or species, will flourish at either end of the spectrum in terms of relative humidity. And what most of you hopefully will have noticed is pretty much around the middle, most of that lot find it impossible to exist. Coincidentally, shock horror, you and I are most comfortable at 50% relative humidity. So what we're saying here is actually controlling the relative humidity which comes with engaging with thermal performance of our buildings and ventilation and so on, actually can give us a built environment that is far more comfortable and far more healthy than we used to. Just taking mites, okay, so dust mites, the prevalence of asthma is directly related to the increase of dust mites, which have generally proliferated since our houses have got warmer, because also the relative humidity has gone up because of bringing extra moisture in. And dust mites generally multiply it massively at over 70% relative humidity. And a lot of us are actually allergic, sadly because it's a bit gross, to dust mite feces. And that's why we've seen so much increase, particularly since the 1970s, of asthma directly related to mites. You control the RH and you will just see the proliferation die off, because they cannot proliferate, which is to do with the way they feed and stuff. And I won't bore you with that because it's a bit gross as well. But anyway, that's key. And the same with fungi. Interesting with viruses, things what we've just been through, and so on and so forth. So get your ventilation sorted is really important. So at the very least, localized ventilation in your wet rooms. So that's your kitchen, your bathroom. If you can join it all up by bringing air into your dry rooms, so your bedroom, your lounge, and so on, and taking it out through your wet rooms, then even better. And generally, if you tie that in with your energy strategy, so if you're going through for a super performance building, such as Passive House, then you really need to look at ventilation with heat recovery, because you're chucking too much warm air out. But means your fabric needs to be really good. There's no point having MVHR if you haven't got air tightness of below 3, because the fan's going to have to work so hard just to keep up with the air that it's moving against the air that's leaking. The air energy that you're saving by not chucking the warm energy out will be lost with the energy you're using for the fan. So keep it simple, but ventilation is important. So ventilation, labour over. Building fabric, this dynamic still is important. And it's not just moisture, liquid moisture in our fabric, remember, it's also relative humidity. High levels of relative humidity, so about 80%, you will find that fungi start to proliferate. If it's timber, it's about 20% liquid moisture, 80% moisture vapor. Also, chemical interactions are much higher the further up the RH it goes. So again, breakdown of materials and all sorts of other stuff can take place. So quick kind of overview, and you're pleased to know we've kind of peaked and beginning to drift into land now. Moisture control in buildings, what we're saying here, key things that we want to be thinking about in terms of the moisture control is heat input. So obviously, if we increase the heat, we're going to decrease the relative humidity, okay, depending on what the levels are already. Ventilation is key, because we want to make sure that we're getting rid of the heavily laden, warm, moist air and bringing in cooler air, which if it's about 70% RH, you'd say that's a bit high, but that might be only 5 degrees and you're going to warm it up by bringing it in, in which case what happens? Well, the RH goes down, doesn't it? Because you remembered from earlier. And then the other one is to do with the vapor and thermal performance of the building fabric. And it's worth noting as well, don't forget that if we're getting moisture building up in materials that are hydrophobic, so which is where they'll build up more, or buildings or thermal performance materials that trap moisture, then actually the very performance of the fabric is going to start plummeting, because it's going to have trapped moisture, which like lots of it, which is going to conduct more heat away from the building fabric. And again, I mentioned this earlier, but here's the map to show it. It's context in terms of where the properties that are in the UK that you're dealing with, because a solution that might work in Peterborough isn't necessarily going to work over in Aberystwyth. So the further west you go across the UK, just to repeat myself, the higher level of driven rain. Cavity wall insulation worked very well in sort of Midlands, home counties, up the east coast of the UK and so on. It did not work well in Wales because too much moisture got driven through the outer leaf. Cavity walls were not built to keep the weather out, folks, just in case we've ever thought they did. The solid masonry wall did just fine, thank you very much. And if it was a bit bad, then you rendered the outside. It was simply a cheaper way in the UK of building buildings. You had a cheap brick on the inside, a more expensive facing brick on the outside. Somebody invents the cement block, pence per block, happy days. Okay, so that's really the main driver for a cavity wall insulation. Kind of useful because there was a cavity there to fill, but there's often a lot of stuff, as we know, already in them. So cavity wall insulation is not a panacea or a silver bullet, and particularly when it comes to high levels of driven rain, that's where you had a lot of failures. I think there's more cavity wall extraction companies in Wales than there are cavity wall installers these days, sadly. But it's important, again, just to understand what we're getting ourselves into. So hopefully you've got some background. Hopefully you're not worn out. Hopefully it's been of some interest. A bit of a summary on design guidance, trying to bring what we talked about together then in some simple bite-sized pieces. So the key with any building fabric is we're trying to balance moisture sources with the way it dries out, okay? And that's the only real way of making sure that we manage this moisture. Going down the route of sort of a bit of a king can you keep the tide out, which is let's just make sure that moisture never gets in, is practically impossible. Okay, there are some localized areas you could do that successfully, but they're few and far between and highly expensive. It's pointless, particularly when refurbing a building. So actually, what we really just need to make sure, very simple, does the building fabric rather dry out more quickly than the levels of moisture that are going into it? Sounds simple, but it's amazing how often that isn't done. And therefore, repeating what I've just said there, it's about regulating moisture, not about preventing moisture. Moisture will get in your building, okay? That's fine. You just want to make sure it stays at safe levels, okay? If you're sat at a table, a wooden table right now, probably the amount of liquid moisture, the amount of water that's making that table up is about 11%. You know, we're quite happy with that. It's no big deal. So having water in our fabric and around us, I mean, it's fine. It's just making sure it's not too wet for too long, okay? So when you're designing a building, to avoid the risks at the design stage, think, can the building components or the build-up dry out if it gets wet? And if it's going to get wet, how is it going to get wet? So when you're looking at assessing an internal wall insulation project, one of the first things you should do before installing is actually assess the outside of the building. What's the rainwater goods like? Are my gutters intact? Have I got any broken down pipes? What's my masonry looking like? How's my mortar joints? Is there any hard standing that's wasn't probably put there when the house was built and is actually trapping moisture evaporating from the footings? Do I need to put a French drain in? That's all part of a building, you know, makeup, and something we need to be careful of. I said this earlier, is its capacity to dry out equal or greater than the moisture actually entering the fabric? And the materials that I'm using, so are they vapor open? Have they got hydrocophicity? So that's the ability of buffering moisture, which is quite a neat one. So it's, again, there's no problem taking on moisture. It's just, and that's actually quite a useful dynamic because it will take it and then let it go again. A bit like floodplains, if you will. If you think about where a floodplain exists, you know, the whole idea of a floodplain is the river bursts its bank, dumps its energy, is far less destructive, and is only there temporarily, and then river gets itself back together. Why? Because the rain stopped. So it's a similar kind of thing with buildings. And then capillarity, again, that's ability to wick moisture. So much more helpful words are the buffing and wicking of material, because then if it's dispersing, a bit like our piece of blotting paper earlier, it'll dry out more quickly. And that's this drying out potential that we're kind of looking for. Okay, we're nearly there. So I'm going to go through some examples from Unity, but which just kind of help to bring it together. But it might be worth just stopping momentarily for a quick Q&A if anybody's got anything.
Yeah, there is a question from Stephen. And Stephen, I'm not going to try and read your question out because I don't fully understand it. I want to do it justice. So if you could come off mute and maybe ask it yourself.
Yeah, sure.
You're still there?
No, I was going to say, just basically, which I wasn't sure I was going to come on to in the following slides, just basically any case study costs of doing it and whether retrofitting older properties, on whether they have to be done completely in one go, obviously to avoid any damage to the associated building fabric, and doing it in one go may be cost prohibitive to many people.
Great question, Stephen. Thank you. I'd say two parts to that. One is if it's an external solution you're using, again, keeping on the theme of solid wall, then generally, yeah, you pretty much want to hit that in one go. There are circumstances you might be able to isolate elevations, but it's by the time you put scaffolding up and everything else, you may as well just hit the whole thing in one hit. I think one of the benefits of internal wall insulation is that you can actually do a room at a time within reason. There's a couple of circumstances you want to be a little bit careful of. So if you insulate an internal wall heavily, and then you've got a partition wall, also made of solid masonry, that abuts the external wall, you may get a temperature drop of a sort of high, sort of a too great a temperature drop, the other corner of that wall, which then you may find you start to get condensation on. That is quite unusual, but it can happen. So if you're getting involved in a project like that, just get the right advice. And in terms of costings, I think there's two parts to this question. If people often just look at it purely in financial terms. If I spend £5 now insulating my property, I'm not going to get the payback for another 10 years, and I'm thinking of moving in 3 years' time. And it's like, well, yeah, but the difference is you're going to benefit immediately. So if you're driving a car with solid rubber tires, okay, and I said, I'm going to sell you these amazing pneumatic tires, it's much more comfortable, okay? And then you said, yeah, but you know, oh, and you're going to save a bit of fuel with them, okay? And you said, yeah, but looking at that price, it's going to take me 5 years before I save the fuel. I bet that if you put the tires on your car, you'd be like, I'm not going back to solid tires, thank you very much. So the level of comfort that you get is immediate as soon as the work is done. And I think we need to be aware of that. And with that comfort, if it's done properly, can also, for some people, it's health as well. There's a tenement block in Scotland where the people were moved out because they needed to renovate the property. The property was renovated properly. It included thermal performance and all the rest of it, measures. And when they moved in, it was noted that there was a marked improvement in health to a lot of those tenants. Some boffin worked out somewhere that the improvement to health of those individuals who'd moved back in would have paid for itself. I think it was something like within 18 months against the NHS. So the cost of the improvements, okay, I'm sure I could put that sentence together properly better, but I hope you got the drift. Basically, the saving to the NHS after 18 months to those people who were originally ill because they were improved in health would have effectively paid for the refurbishment of the whole of that tenement block. So it's we're not joining the dots up properly. But I'm getting off your question again, Steve.
No, it's just basically if somebody's going to be renovating their property, they tend to do it in stages. It's like you probably do a kitchen, you probably do the windows. Yes. And it's my hesitation with the way the government push the drive for retrofitting a lot of old properties, and especially with the amount of old properties that are in the country, there's not going to be the amount of people out there that can do it in one go. And like I say, a lot of these retrofitting companies may compromise the rest of the house structure by only doing sections of what people can afford. That was the I probably didn't put the question across properly.
No, that's fine. So the short answer to that is no. With internal wall insulation, so long as the system is appropriate, and there's a lot of systems out there that aren't. If the system is appropriate, then actually there's no reason why you can't do it in stages. I can actually testify to that myself. So I've got, I mentioned earlier, I've got Victorian property, and the majority of the rooms are now insulated, but I've been here for 5 years, and there's about 3-4 that aren't. And it is cool, other than the fact that they're a bit cooler or you need a bit more to heat them. Actually, there's been no issues in terms of damaging the property whatsoever.
So you haven't witnessed any detrimental mould in those rooms in any way?
None at all. No.
Okay, that's fine. Thanks.
Yeah. No, pleasure.
Right, the questions are flowing in now, so I'm probably going to say we'll take the 3 we've got, and then we better call it a day. Jaya says, would then insulating a garage internally to bring it into residential use need additional ventilation or air bricks if it has 3 external walls and hence quite a lot of internal insulation applied to it? It has 3 external walls and so a lot of retrofit insulation to bring those walls up to standard.
Would it bring it into?
Would it need extra ventilation or air?
Oh, I see. No. Well, no, not on the. Yeah. is it a cavity? If it's a cavity, that's why you'd normally have air bricks.
I wasn't sure about the air bricks.
Yeah, your air bricks are normally there to ventilate a cavity so that you don't get a buildup of moisture in the cavity. If you've got a cavity, I'd be careful about putting internal wall insulation on the inside. It can work. The main thing really is, I think in terms of ventilating, I would look at ventilating the internal property. So if you're taking a garage, then you just want to make sure you've got decent extraction, and it depends on how many water source or rooms that produce water sources, so bathrooms and stuff like that you're putting in. The other thing as well, if it's a garage, it might only be a single brick, so you really want to be careful. That would be my main thought.
Yeah, don't think of the room in isolation. In other words, how do you improve Y? A very quick one from Sarika. How do you improve Y value?
Yeah, so Y value is all about detailing. So it's remember again, it's the interface usually between two elements. So just think about how, where a wall hits a window, you think about how thick your insulation is, where it's going, making sure there's a continuity of that. That's usually how you do it. Externally, if you think about it, that's quite a neat way of looking at it. External insulation is a bit like a tea cozy around a building, and so often you're killing a lot of those thermal bridges off, particularly the way if you did it, say, with a timber frame building on a new build, so long as it was the right insulation. So that's generally it. It's understanding the detailing and treating accordingly. Thank
you for that. Finally, a question. Answer it if you want, or I will if you think it's more allied to building control. Is a residual cavity of 50 millimeters or 25 millimeters for some PIR insulation products essential in the east of the country, i.e. London, where driving rain is limited? So do we need a residual cavity with PIR insulation?
Yeah, the 50 mil, Denise, is more to do with making sure, because when you build a cavity wall, you end up with the ties, and then as you're building, the cement or mortar, whatever, goes down between the cavity and gets stuck on some of the ties, often described as snots, quite another charming term, which can then end up building a bridge. And then if your cavity isn't 50 mil, you often find that and the width of the cavity, you don't get a proper cavity fill. So it's to do with the way it gets blown in is usually the issue. Unless you've got something else to say on that, Trevor.
Well, yeah, I mean, I remember, I'm old enough to remember when partial cavity insulation came in, and exactly what you say occurred. Those cavities were bridged. Nobody could build them carefully enough to keep the mortar droppings from bridging the cavity. Regulations and the approved documents suggested that residual cavities should be at least 50 millimeters, but products were available that had been tested by the Agrimon board and companies like that and certified for use with only a 25 mil cavity. And if it's done carefully, using battens in the cavity as you build them to make sure mortar droppings don't accumulate, they can work, and the insulation is clipped properly back, they can work. But the bricklayer has to be a good one, and he has to be very patient. So the answer is yes, you can, but you've got to be very careful, and you've got to use a product that's tested and certified. Of course, there are now full fill PIR insulation products that you can get as well, which are designed with corner pieces, and again, they're a fiddle, and I think builders hate them, but they're out there. Just look at what the manufacturer's recommendations are and check that it's certified for that use. That's my answer. Nice. I noticed, Jay, I hope you pronounced your name right. You said no cavity. So really, if you've got an air brick, you're going to let a lot of heat out. So I'd say no air bricks, just other forms of ventilation, more controlled. Conscious of time, so probably should crack on. Hopefully you can see the slides. So a useful insulation material, which is less familiar in the UK, but much more prevalent in mainland Europe. Sorry, Trevor, I thought you said something. Is something called woodfibre insulation board. So this is what it looks like, and it's quite a neat product. So when you chop a tree down, you lose all the crown and stuff that goes to waste. Then you've got the main sections, and then you obviously chop that up into useful sections of timber, but you're usually left with a pile of chips. About 50%, in fact, is a pile of chips. So it'd be a neat way to do something with that. You could burn it, and as part of
a cycle means you, yes, of course, you're releasing CO2 in the atmosphere, but hopefully as long as the trees are growing more quickly than you're burning, you'll be fine. So it's not a bad use of wood chip. But another alternative is taking wood chip like this, heating it up under pressure. So the chip's on the left there. When heated up under pressure, that softens the glue that holds the cellulose together. So timber's mainly cellulose and lignin. That's the glue. The lignin softens, and then when you throw it through these metal plates, it fiberizes it. So you end up with long strands of cellulose. If you start at number 2, so we've just sort of fiberized it, you then throw it through a flash dryer. So you've just got these cellulose strands. Then you can actually then throw a bit of only about 5% bonding agent into it. So a bit of PMDI. It's a bit like the stuff if you've ever cut yourself and they take you in an A&E and then glue you back together on stitching. It's the same sort of product. And then you create slabs of wood fibre out of it by compressing it. And as a result, you basically created a slab of insulation. So very, very briefly, insulation primarily works because you've trapped air. Okay. So effectively what the wood fibre is doing is it's trapping the air both between the fibres, but also the fibres themselves are hollow. So you reduce dramatically the amount of heat loss you get from across the material if you've managed to trap the air within it. That's how double glazing and triple glazing works. So there are a number of different types of wood fibre. There's the flexi stuff, which normally goes between rafters and joists and stuff, and is probably the one that's most similar to, say, a mineral wool bat, by example. It's denser, so it's better acoustically. And also you've just, one of the key things with the wood fibre is it's cellulose, so it's carbon. And the carbon was created by sucking a load of CO2 out of the atmosphere. So you've actually just locked up a load of carbon. So a pallet of the semi-rigid board, in fact 2 pallets, sorry, not 1, is about a ton of carbon, or a ton of CO2 rather, sequestered out the atmosphere. So that's quite a neat thing that we could start to do by actually improving the amount of timber-based products that we use within the construction industry, and thereby sequestering more and more CO2 out of the air. That one's a square edge, that one's a profile, which is quite neat, because it means if you're going over something like joists and so on, you're not having to hit centres of the rafters and so on. At a join, you can actually have the join part way across. Now, traditionally, and rather unhelpfully, we've gone for a vapor-based check type approach, which I mentioned earlier, this idea of just trying to keep the moisture out together. So we fit some insulation to the face of the wall. We're concerned about the fact that we've got moisture coming through. And if you remember earlier with the RH discussion that we had, this wall is now going to be colder. Why? Because we put insulation on it. So the same heat load that's inside the room is not going to be coming in at the same rate. It's still going to get heat, just not as much. So it's not difficult to think that this could be 9 degrees C, back to our previous example. And therefore, there is a risk of getting interstitial condensation exactly where we don't want it. So the way the industry used to work was to say, oh, don't worry, we'll stick a plastic bag on the inside to try and stop moisture getting in altogether, and that works. The frightening thing is if you try that with, some of you may be very familiar with something called a dew point calc, which is based on the glazier method, which in its own right is fine. It's just not the right tool for this particular dynamic, because all it's doing is measuring moisture vapor. So to give you an example, if you were to build a timber frame house, 200mm stud, insulation between the studs, a vapor barrier on the inside and plasterboard in the inside, and then on the outside you decided to stick plasterboard as the weathering surface, you then stuck that property in Orkney and faced it out into the Atlantic, according to a dew point calc based on the glazier method, you'll be fine. Now, hopefully most of the people are saying that's ridiculous, it'd be a soggy mess, and you'd be absolutely right. So the point is, it's not that the glazier method's wrong, it's just the wrong tool for the job. You're just measuring vapor pressure getting out of the building and then saying, well, if we had a vapor check, we'd stop the moisture in. In reality, if you take a VCL, as we generally call it these days, vapor control layer, which is closer to a vapor barrier, so very low in its emissivity in terms of the amount of moisture let through, so we call that an SD value. So in this case, an SD value of 2, it will only let about 5 grams of water through on a winter's day per square metre, which is tiny amount of moisture. If, however, we were to cut a slit down that only 1 millimetre wide, over a metre length in a square metre, you'd let 800 grams of moisture through on a winter's day per square metre, which is a factor of 160, as it says on the slide. That's a huge amount. Now, you're not going to have a problem tomorrow, but you will probably have a problem in about 4 or 5 years' time, because you will have had a constant buildup of moisture that's got in and hasn't been able to get out. So really, the effectiveness of VCLs cannot be guaranteed. And I'm not saying never use them, because they can be quite useful to slow down the amount of moisture getting into the fabric, but they should never be used to prevent moisture getting into the building fabric. So it's important to understand. So that's our vapor-based check system. The issues here as well is it doesn't take account of reverse diffusion, so the wind-driven rain scenario. So you end up potentially with moisture building up on the back of the vapor control layer as well, in addition to potential interstitial condensation that perhaps can't get out because there was a gap in the vapor barrier. So even if the vapor barrier was fitted perfectly, or the vapor control layer, I should say, was fitted perfectly, there is still a risk that you could end up with excessive moisture levels. And you also haven't taken account of ground moisture, subject to whether there was a DPC, subject to whether or not it was balanced. Previously, if it was balanced, that was because moisture was evaporating out into the outside and also out into the room, and the ventilation in the room was dealing with it. Now, there's a risk that because you've sealed it up, you're getting further issues of moisture buildup from the third moisture source that we talked about earlier. Alternatively, vapor open system, you're getting the same forces of moisture. The difference is because this doesn't have a VCL and it's got these abilities to wick buffer moisture and is also moisture vapor open. If you do get interstitial condensation forming within the material, it's more likely to form away from the wall, and then it's more likely to, well, it just does. It then disperses out into the room by capillarity, because capillarity works more quickly than vapor openness, and as a result regulates much more effectively the levels of moisture that's within the system. The same if you've got the source of moisture from the ground as well, that's also going to allow it to move out more. If you've got damp on the wall before you fitted it, then you've got a bigger problem. We're just talking about not upsetting a house that is already in equilibrium. Same thing applies. One system that might work, you know, if you put 100 mils on a wall in Cambridge, it's a pretty dry climate, whereas 100 mil, you know, in Bala in Wales, different climate. So you need a proper assessment. So again, from a design point of view, we'd recommend getting something assessed such as Woofy or Woofy Pro, which is a dynamic moisture model. So it assesses the liquid moisture as well as moisture vapor. It assesses it against the local weather data, not just a generic data, and it measures it on a monthly pattern. And you generally model it for about 10 years and check that it's not a 10-year time period, but the model shows 10 years. And you're looking for it to make sure it dries out to safe levels once it's been installed. Make sure you get your details right. Make sure the contractors are trained properly. Make sure you're getting enough site support. All these are key parts to any retrofit. So a quick checklist at the end, because I'm conscious of time. Regulate moisture. It's not about preventing it, it's about regulating it. So avoid barriers. They generally don't work. If you're relying on a barrier to be a barrier, it won't work. If you're relying on a barrier to slow things down in terms of moisture coming into the fabric, that can work. Just be careful. It can be quite useful. Fully bonded. So no gaps between internal wall insulation and the wall that it's going on. The gaps are a breeding ground for mold because you've got oxygen, damp, and just enough temperature to make them happy. So no gaps, fully bonded system. That's absolutely key. Get a dynamic moisture assessment. We talked about Woofy earlier. Most systems in the marketplace that are more breathable, like the ones that Unity do, generally they've been assessed for certain areas already. So they'll usually give you a green or a red light. Well, they usually give you 3. They'll say a green light, it's absolutely fine. You don't need to worry about it because we've assessed enough of these to know it's fine. A yellow light, okay, no, actually we'll do an assessment. We'll just check it's all right. Or a red light, no, this just won't work. It's unusual. The good thing about Woofy is it even actually tells you which elevations do and don't work. It works on elevations of building, not just on any old wall. Make sure you've got appropriate room ventilation. If you're putting internal wall insulation into a bathroom, There are issues. Be careful with tiling straight onto it, but that's up to the manufacturer to explain that. But for goodness sake, make sure you're actually ventilating the room properly, even if it's just local extractor fan like we talked about earlier. Understand the interfaces. Okay, the details are key. Sills, as in the window sill. You want to make sure that you've got some insulation potentially under there. Reveals, we talked about those a lot. Joist ends are important. If you've got a joist going into the wall at 90 degrees, you'll probably have a gap around it over the years. That means that warm damp air that we talked about earlier at 50%, well, it's not damp initially at 50% RH, as it moves down the gap in the joist, that joist, the air around it's going to get colder. It's going to be colder than it was before because we've insulated, so the wall itself is going to be colder. There's a risk that moisture might start falling out at the end of the joist and the joist rotting out. So joist ends are important. Make sure that any gaps that exist between the joist end that punctures a wall and an external wall that you're internally insulating, make sure that that's got either dubbed out with a plaster or maybe something like an airtightness tape. And typical build-ups. So this would be how you would apply this particular system. So we've got the wood fibre board, which is the green stuff. We bonded it, so we stuck it to the wall with a lime-based product. So this is this whole quest for no gaps. The benefit of lime-based products as well is they're highly alkaline. Mold doesn't like alkaline, so that's another kind of way of helping to prevent any negative situation. If the wall before you put it on had gypsum on it, there's a bit of the jury's out on gypsum actually. People are concerned it's going to turn to salts, so it might be worth removing it. Certainly if the plaster that's on the wall is already knackered, remove it, in which case you've got quite a rough surface, so you'd want to just dub that out first just to make it a bit smoother before bonding on the wood fibre. And then on the inside wall, you're looking at a base coat and a skim coat, or you could batten out to create a service board and then put a plasterboard on. Gypsum on the warm side of the room isn't an issue. People sometimes say, oh, gypsum isn't very breathable. It's breathable enough in this context, so it will let moisture through. It won't basically accrue a moisture buildup within your fabric. Consider airtightness tapes at the appropriate junctions. So on this particular slide, we were looking at the interface between the window frame and the window reveal, because sometimes you might get a bit of gaps there, etc. It doesn't take much of a gap, by the way, for air to leak out. We do microscopic, you wouldn't necessarily see it. Obviously, insulate your reveals. If you don't insulate your reveals, you're almost guaranteed to get mold growth on those because you're getting condensation because the wall's cooled down, because you put internal insulation on. Insulate under the sill, we mentioned that earlier, and other airtightness tapes, which might be considered depending on your builder. Wet trades, plasters are really good at delivering airtightness. You don't need to just rely on tapes and membranes, but just think about the continuity of your airtightness layer. This is what it looks like bunged on the wall, a bit more than bunged. There's a lot of fixings on there. You don't always need to have quite as many fixings, but these fixings themselves are what we call thermally broken. So they're made of either solid plastic with two parts, or there's a metal pin in the middle of them, which gets driven into the wall. But then the contact with the inside is then broken with a further plastic piece. Otherwise, you end up with a load of black dots on your wall. And just so you know, this is used quite prevalently. This is a Grade 1 listed building, which had internal wall insulation applied to it. It's Trinity Court, Cambridge. It's called New Court, apart from it's not new at all. And it's in Cambridge, and it's this was really important. Historic England got involved. They were a bit concerned because it's this Grade 1 listed building, and how could we possibly stick insulation on it? That's really bad. And only a handful of buildings in the UK, so I think it's about 400,000, are actually Grade 1 listed. And then so just go and fit it on other buildings, basically. That's what they said to the university, until the university pointed out the fact that most of their buildings are actually listed. So they've got to do something. And eventually, when English Heritage were, when this whole moisture issue was explained, and they could see clearly that this wasn't going to damage the building fabric, they were happy to go ahead with it. Also, because the primary thing, frankly, about a building is making sure that it's habitable, because if you do use it, then it will stay people will keep it, it will have upkeep and it will be looked after. much more than if the building's not in use. So this was quite key. That's a quick internal shot, but I'm conscious of time, so I'm going to go to the end. So I hope, like I said earlier, I might really warn you right now. Hope that was useful, and hopefully, yeah, like I say, hopefully a benefit. And I've lost my team, so I can't kill my slides. Bear with me. Okay. Good. Any final questions?
There are a couple of questions, but I think we're going to have to wrap up now because of time.
Yeah,
so,
absolutely.
Andrew and Ian, don't worry. As always, any questions we don't deal with on the day, we'll deal with when we follow up with a mail shot. So your questions are good ones, and we will answer them. So time remaining. Thank you very much, Andrew. You know, that was worth watching twice. Actually, really interesting again. Really thought-provoking. Everyone can go and have their tea with their families now and say we did some CPD, which was more complicated than rocket science, and really impressed them. So that's got to be good. I also want to say thanks to Tom Perkins, who's in the audience.